Are you really ready? It's time to get this show started. The objective of this video is to help you to make a great show. By now you should have read all of the resource materials, including the grading rubric. This document is very clear on what is exemplary, proficient, mostly proficient, and incomplete in terms of the grading factors of movie quality, physics content, teaching strategy, and creativity. The movie making tips are also a must-read item. And when you have a close encounter with a movie, look around and learn from the masters of the art form. Hold the camera steady. Think about the shot. Think about the angles. And transition from scene to scene to hold the attention of the audience. Create a visual experience. Warp our minds. Basically, is there enough physics to fully explain the topic? There should be careful analysis of the topic. Don't just lecture, and remember your audience is more than your teacher. It's not like reading a textbook or blah blah blah.
Blah 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 blah.
Informative and educational, a pleasant experience. Once again, remember your audience. Think cool Discovery Channel episode. Put your own stamp on this video, of course, but don't be afraid to borrow from other resources. On this factor of grading, use digital media to teach. Make free body diagrams. Use slow motion, reverse motion, or even some combination to show the physics. Unleash the power of digital media to teach. Show me the physics. Creativity includes using some level of inventiveness or original thought, not only to keep the interest of the audience, but in all aspects of the video. Neat whiteboard drawings, animations, good jokes, images shot from different angles, and original teaching strategies are all great ways to teach and entertain at the same time. Sometimes, talented students take this to a different level and will do things like create an original set of animations or even their own soundtrack. What follows is a sampling of some of the best projects ever done. Good luck in showing that physics is truly everywhere.
Hi, I'm Jason Wang and welcome to Physics is Everywhere. Unless you're in a vacuum, sound is everywhere. Take a deep breath, swallow your saliva, and listen to your surroundings. Sound is there, and it's impacting you quite literally. Sound has the power to calm us, excite us, anger us. It's used in arts, navigation, and science. And yet recently, it's also been discovered that sound can also be used to lift a few kilograms of materials. Welcome to acoustic levitation.
This is our acoustic levitation project setup. Now this is the stand that holds everything in place, and this is a transducer, this is a reflector, and these are all connected by the amplifier through two wires, the ground wire and the positive wire.
Intellect and let the rhythm affect to lose the inhibition. Follow your intuition, free your inner soul and break away from tradition. Cause when we be out, girl, it's pulling me out. You wouldn't believe how we wow. Oh!
Motion. Rotational motion is when an object spins. It happens in our everyday life. Biking, opening a door, swinging a golf club, wrestling, dancing, and a lot more. When an object undergoes this type of motion, it rotates about an axis of rotation. For example, the axis of rotation of this tire is the imaginary line passing through the center. In this case, the axis of rotation is a line passing from the top of the breaker's head all the way through his body. Pirouette. A dancer turns the shoulders and the head to help complete a 360-degree turn. Another thing to consider when observing the motion of an object is the moment of inertia. Yes, inertia! Remember Newton's first law of motion? An object in motion tends to stay in motion. An object at rest tends to stay at rest because of inertia. The moment of inertia is very similar. It describes how the mass of an object is distributed and how it affects its rotation.
Oh, you!
Huh? That looks easy. I can totally do that. Here, hold my milk.
Did you guys say football?
Whoa! Can you teach us about football?
I sure can.
So now, let's look at directional vectors and how it directly relates to getting the football where it needs to go. Almost 100% of the time, quarterbacks don't have the luxury of being able to throw the ball staying still at a still target. If the quarterback doesn't move, he will get tackled. If the target doesn't move, the ball will be intercepted like this. Thus, to prevent interceptions, everyone is moving. There are several factors that come into play once everyone starts moving. First, we have the vector of the ball as shown. Then, the vector of the quarterback. These two vectors added up make the directional vector of the ball. But then, there's the final vector of the wide receiver. Here, the wide receiver is hoping his vector will intercept with the directional vector of the ball so he can catch it, like so.
When any liquid interacts with a surface, we can observe properties that are truly unique. For example, we know that when a liquid is placed into a container, it takes the shape of that container. Yet unlike a gas, it does not change in volume. Superhydrophobicity is another one of these unique qualities that we can observe when water or any liquid interacts with a special type of surface. We can make anything hydrophobic. Well, this company made a spray that does just that. And since this is a physics project, there's plenty of physics involved. We've compiled a few video excerpts to show you how this kind of spray can make almost any surface repel water. In this first particular demonstration, we see the colored water roll freely off the face of the cinder block because the repulsive force of the superhydrophobic coating is greater than that of the concrete. Switch gears and go back into the physics. More importantly, what makes the scientific difference between mere hydrophobicity and, once again, superhydrophobicity? So we've all seen what water looks like on a standard surface, and now also a hydrophobic surface. But what about the super hydrophobic surface? How do we ultimately tell them all apart? The water doesn't simply try to ball itself up anymore, but it actually tries to roll off. Furthermore, you may note the slightly more pronounced spherical shape the water now takes, once again due to our good friend surface tension.
Oh yeah, it's you turkeys. What do you want? Oh, so you guys want to So what do you say? Well, if it's for good deeds, yeah.
Then let's get started.
How did you manage with all that jumps, flips, and rolls without getting hurt and still be able to keep up with our feet?
Well, just simply by applying some simple basics in it. With that stamina of yours, you guys only need to understand some basic concepts of physics involved in free running, such as momentum, rotational force, projectile motion, forces, and impulse.
Impulse?
That's right. When a free runner lands from a high elevation, the force obtained from the land needs to be reduced in order to decrease the impact. The force is not only absorbed by the knees, but also by the back of the neck, on the back, the shoulders, and arms. It extends the time of impact when doing the roll, instead of taking in all the impact instantly flat feet first, thus creating greater impulse and reducing damage done to the body.
And what happens if you don't roll?
And our cameraman, Owen Zhang.
So, let's cut to the chase. Today, we'll be learning about non-Newtonian fluids. So get ready to gain some psi knowledge.
Stress describes the creation of tension through the application of a force on an object, the result of which is known as strain.
When force is applied to common, regular liquids such as water, it is met with little resistance and therefore shows few signs of strain. For example, when one jumps into a swimming pool, he or she easily travels through the water and into the pool, and is not met with much resistance. However, non-Newtonian fluids act differently than regular fluids, and, depending on the type of non-Newtonian fluid, the outcome can vary quite drastically.
Non-Newtonian fluids change viscosities or flow characteristics when stress is applied. Depending on the type, if you apply a force to such fluids, for example, if you jumped into a tub of one, the sudden application of stress could cause the fluid to thicken and display the physical properties of a solid.
So another example of how it acts like a solid is when I punch it, my fist doesn't go through. I can punch as hard as I want, but I'll never make it through. But if I slowly enter my hand in, it'll seep in.
Oh, come on!
Your mission is to take a selfie with the dominoes located in the TV room. But before that, listen to these explanations on physics concepts of Rube Goldberg.
Energy is everywhere, and as it goes down, it gets kinetic energy. The energy transformation between can be explained through the falling dominoes.
Next, centripetal force. Centripetal force causes motion in a curved path. It also means a center-seeking force. In the animation, without the block, the ball will continue on in a straight line. But with the block, which represents centripetal force, the ball would curve with the block so it changes direction. This can be seen in the marble run where the marble goes around the loop. Also, looking at the equation of centripetal force, which is F equals m times v squared over r, the v squared is proportional to the force. So in order for the marble to go around the loop, it must have a large velocity. That's why the marble was on a higher track. It's because then it could gain a larger velocity to go around the loop.
Copy that.
Cameras. They capture the moments that make up our lives. The moments we want to remember, and sometimes the ones we don't. Our very first Barbie sing-along songs. Our first bowls of noodles. Our first Halloweens. Our first accessories and trips to the beach and popsicles. Our first years of childhood. Years filled with 4th of Julys and beach vacations. The years when we annoyed our siblings, played with our stuffed pigs, and flaunted our plastic sunglasses. Messy faces and pink poses and silly afternoons. Our goggles and fun in the sand, princess costumes, and tricycles. All of them, frozen and saved by the amazing things we call cameras. Without them, our minds would grow older, and we would forget about the wonders of years past. But cameras save these small snapshots, these little insights into our lives. So the truth is, when we really, truly think about it, cameras don't just preserve images, they preserve memories.
But how did these cameras become the ones we know and use today to capture our memories? To understand why we are able to take photos today, we have to go back in history, back to when the camera was first invented. Although early adaptations of cameras were used dating back to 1000 BC by various scholars, philosophers, and mathematicians, the camera closest to the most rudimentary model we recognize today is the camera obscura.
First, the light travels through the main camera lens and it hits the mirror placed behind the lens. The mirror is constructed and placed at an angle that allows the light to reflect and refract upwards. At the top of the camera, 2 more mirrors are placed so that the light travels in a path that resembles the number 4. The light then is directed toward the viewfinder, where the photographer may look into in order to see the image that is seen through the lens.
I don't even know if I would refer to skateboarding as a sport. In skateboarding, there's no rules.
There's no goal, there's no limitations. No one's ever going to tell you that you're bad or that what you're doing is wrong, because it's completely subjective. You decide what to do on your own, based on what you think is cool, or what you think would be the most fun. And that's what makes skateboarding amazing. In addition to its personal value, skateboarding is the quintessential demonstration of physics in action. Like other sports, it involves constant movement, but the movement is in the air or in contact with obstacles. Because of these qualities, skateboarding perfectly illustrates energy and friction. Let's start with energy. Energy can be explained as the ability a physical system has to do work on other physical systems. While energy can be transferred from one system to another, or from one form to another, it can never be created or destroyed. This is known as the conservation of energy principle. As we see here, pumping up and down the half-pipe transfers one type of energy, gravitational potential energy, to another, kinetic energy. These are the two types of energy I'll be explaining today, as they are the most apparent in skateboarding. Gravitational potential energy is the energy associated with an object due to its position relative to a gravitational source. It is calculated by multiplying the mass of the object, its free fall acceleration, and its height above the gravitational source. For example, here I am, weighing about 80 kilograms on top of a 5-meter half-pipe, on planet Earth, which has a gravitational strength of approximately 9.8 meters per second squared. The product of those figures equals the gravitational potential energy I possessed at that point in time, which is 3,924 joules. Kinetic energy is the energy of an object due to its motion. It is calculated by multiplying 1/2 the mass of the object and the velocity of the object squared. After I drop into the half-pipe, I am moving at approximately 9.2 meters per second. Plug that and my weight into the kinetic energy equation, and we get 3,386 joules. According to the conservation of energy principle, my gravitational potential energy at the top of the ramp should be the same as my kinetic energy at the bottom of the ramp. Yet there is almost a 600 joule difference. The explanation for this discrepancy lies in our next topic, friction. Thanks for watching. I hope you enjoyed yourself and learned something new.